All right, so let's get started on section 3.2, exponential functions. And I kind of wrote over here, an exponential function is basically going to be something like, here's a number, 2, 3, 4. It could be irrational numbers as we go forward. It could be anything. This is called the base. And now we're going to read the variable is the power. So we're going to look at like 2 to the 1, 2 squared, 2 cubed, and then see what this thing looks like. Turns out it's a function, so it passed the vertical line test. And as we go forward, we'll see that it's 1 to 1. It passes the horizontal line test. Sounds like it's got an inverse, and that'll be the log function. Okay, so let's get started. We're going to do about the graphing to start with and kind of get an idea, of how these things are going to look. This is the basic graph. This is a positive number. This is always going to be positive, but this is assumed positive, but we can look at negative exponents and just variations of those. Okay. So previously we looked at things like y is equal to x squared. So we looked at this exponent, but the exponent was fixed. The x was the variable. And now we're looking at, here is this like a coefficient, but it's the base that is fixed. We're going to have a whole family of these things depending on what the base is. But we've got two versions. This is the base greater than 1. We can also do the base less than 1. Bigger than 0, it has to be positive, it has to be bigger than 0. If I'm just looking at 1, if the base is just 1, 1 to any power, 1 to the 10th, 1 to the 20th is still 1. So that's just going to be a straight line. It's not very interesting. Okay, and it would be 1 to 1 as well. Okay, here is another variation. Here is y is equal to 3 to the x minus 1. So we can do operations in the exponents. So this looks like 3 to the x shifted right by 1. And we'll kind of look at stuff like that. So that's kind of a horizontal transformation problem. Okay. So the exponential function, let b be a constant real number such that b is greater than 0. You can't have like a negative number and do it to a power and it just bounces all over the place. If it's even, then it would be a positive number, and if it's an odd exponent, then it would be a negative number, so this thing would be toggling all the way through. And so we just restrict it. All we're talking about is b greater than 0. So let me put the full version is that b is greater than 0. There's going to be two classes between 0 less than b less than 1. It's going to look a little differently, and then b greater than 1. Okay, so there's actually two separate classes that we're going to have that's going to look like two separate graphs. Okay, this is an exponential function. F of x is equal to b to the x. Exponential function, this is what it calls the exponent is the variable, and the base is b. Okay, that's the number like 2, 3, 4, 5, whatever we need. So if it's 2, we're talking about doubling type things. The basic graphing of this thing is that if you were just doing basic graphing, I kind of do like this. So I say, here's my x, here's my f of x, and this is equal to 3 to the x. And I can have negative exponents here. So this is really, so I'm going to go like, I'm not going to do very many, just to get you started. 1 and 2. Okay, let's just go with those. Okay, and we'll see what's going on here. So this, if I'm going to go f of negative 2, this is 3 to the negative 2. So that negative 2 goes into my x. Well, that is 1 over 3 squared, which is 1/9. Okay, so this is 1/9. And then negative 1, 1 over 3 to the 1, that's just 1/3. F of 0 is equal to 3 to the 0. This, I want to put a little dash line around here. This always occurs. For an exponential, the basic exponential, when it hasn't done any shifting, when I look at it 0, this thing goes to the y. This is my y-intercept. And then f of 1 looks like 3 to the 1, which is just 3. And then f of 2, 3 squared, which is 9. Okay. So now I would do my graph, and this is my quick sketch. Here's my x, here's my y. Let me open it up a little bit. So -1, -2, 1, 2 in here. And naturally, this is 0. So for -2, this is 1/9. So this is pretty small here. And then 1/3, a little bit bigger. So this is 1, 2, 3, all the way up. 0 is going to go through that point. Okay, so this is -2, 1/9, -1, 1/3, 0, 1, 1, 3, and then all the way up at 2 is all the way up here at 9. So this thing is basically looking like that right there. Okay. So let me pull up Desmos real quick. So let me go here. Let's pull up Desmos to do a better job. Give it a second. And now I'm graphing y is equal to 3. And now I'm going to do my exponent as shift 6. That's the little caret. And that's now my exponent. So that's how I graph an exponential in Desmos. And that's what it's looked like. So if I do 2, I'm going to scale this thing. So right here, that's the 2.9 if we can get it to stick. Nowhere in here. It's like right there. There. That was the 2.9. Okay. So that's in general. The quicker, this thing grows like crazy, and that's the term exponential growth. When you hear the term, they'll use that. You know, if you're talking stock markets, that's just taking off some stock that's really taking off. This is the exponential growth. Population growth is exponential. Now, the bases are different. So let me kind of do a couple of these things in here. I want to add one. I want to compare these things for these different bases. So here's 2 to the x. That's the blue. It's a little slower. And we can do even decimal numbers like that. So that's going to be even slower. It's a smaller number. It's going to take a little while to grow a little bit. Look what happens down here as well. Okay, but if you have something like, let's go y is equal to 4 to the x. We're going to start out faster, or we're going to grow faster when we're doing. Okay, but they notice that they all go through 0, 1 right there. 4 to the 0 is 1, 1.5 to the 0 is 1. This can be any real number. It's hard to calculate in our head of saying, well, what does something look like? What does this value? What is 1.76 to the 2.3 power? And this, we can't really multiply this times this 2.3 times or 3.3 times. It's got to be done in the calculator, and you just do the very same thing. Instead of squared, you've got to look for something like, here's this, or your calculator may have this, and then you'll just do the 3.3. 1.76, 3.3 in most calculators. Okay, so those are numbers. Same thing, bases, exponents, and then you can kind of go work this thing out. Okay, so one more, and I would kind of do the very same thing, but I'm not going to go through. Here is f of x is 2 to the negative x, and I would go through the very same thing and just kind of show you what's going to happen here. If I go -2, -1, 0, 1, 2, for an exponential, this kind of gives me a good idea of what's everything is going on. F to the -2, though, is 2 to the negative. I've got that negative, and now this is -2. Well, this is 2 squared. Negative, -2, 2 squared, that's just 4. Okay? And then f of -1, 2 to the -1, that's 2. -0 is just 2 to the 0, that's 1. And now this is where we get into the fractional. 2 to the -1, which is 1/2, 1 over 2 to the 1, and then f of 2. That's what that looks like. Okay, so for here, we're kind of doing the opposite, where we're starting over here higher. So -1, -2, 1, 2, 3, 4. I'm kind of shortening this so this is not a good scale, but it'll give you an idea. The -2 is 4. The -1 is 2, 0, 1, 1, 1/2, 1/4. So this thing is really going through. Oh, let me look at the actual graph here. It's here, here, here. This thing is going to go like this and decay. This negative exponent is a decay. The other one I told you was exponential growth. This is decay. And let me go back over here to Desmos, and let's put this back in. I'm going to go 2, and then shift 6 for my exponent, and then -x. And here, this is the decay. I start out with something big, and then I go into a smaller and smaller mode. We know what horizontal asymptotes is. This is the horizontal asymptote. We're getting down to 0. Okay, so here only on one side, if we were growing, that horizontal asymptote, we're going from 0. Here is going to 0, but it's only a one-sided type decay or growth too. We're decaying to 0, and we're growing from 0. Okay, so those are some practices. This is basically, if I look at this, I'm thinking of my transformations. I'm thinking I left shift 2 to the x. So my base function is 2 to the x. Left shift it by 1. So here it's actually go at -1. This is going to be 0. And flip it. So now I'm going to have this thing going like this, and then up 1. Okay, so I can put all of these things in and actually do this calculation. I just want to kind of do it through Desmos again and show you that transformation. Y is equal to 1 minus 2 to the x plus, let me put parentheses, x plus 1. Slide this over, come up over here, and I'm going to do this. Y is equal to 2 to the x. So first of all, I'm going to shift this left, so I'm going to build this one piece by piece. So here, now I'm going to take this base function, shift it left by 1. So instead of being So here is at -1, that's the 0 point. At -1, 2 to the 0, that's 1. So I've shifted that over, and now that negative is going to flip it over across the x-axis, and then all I'm going to do is now shift that up by 1. So that's the pieces that build that out. Okay. Left shift to start with your base. Left shift, reflected across the x-axis. What was positive is negative. What was negative is now positive, and then up by 1. Those are the steps in the transformation. So here's the general. Here's our parent function, y is equal to 2 to the x. Anything here, if a is less than 0, we reflect it across, so we shifted it by h. Right, so if this is positive, shift it to the right. If this is less than 0, that makes that positive, we're going to the left. My scaling, I like to refer to this as scaling, but if it's negative, it's going to be scaled after we reflect and then shrink or vertically stretch. Here's the K. Naturally, we're going to shift up if it's positive, down if it's negative, and that's what builds up that piece. Okay. So I want to do a little exercise here. So we're going to do a base that is frequently used. Okay. And let me tell you how we kind of come about it. Okay, so this property of doing steps and everything comes up frequently in different areas. It just seems to pop up naturally. Naturally occurs during modeling. Okay. And what I want to do is this thing comes up to some power. It's a percentage or proportion here. And I want to know what happens as x gets big. Okay. So I'm going to do a couple of representatives. Okay. I'm going to do, this is x, this is this. So if I do this number in my calculator, one plus 1/2, and that is now squared. If I calculate this thing, this is 0.25. Okay. And now I'm going to go up to, let's do 10th. Let's jump up to a 10 here and a 10 here and see what this thing looks like. And I get 2.59374246, all in calculator. That's the only way I can get these out. Okay, there's no way that I'm going to start giving the decimal number. Now this I can do, multiply whatever this is, decimal number, times itself 10 times, but that's just a lot of work to get a decimal. So this is all calculator work. Now what I'm going to do is jump up to 100. And if I do that calculation, I get 2.7048. And now if I do 1 plus 1 over 1,000, I'm going to bump this thing up and get pretty big here in just a second. This is 1,000. And I get 2.7169. Notice from this to this, there was a big bump. And then from this to this, it was a relatively small. And then when I went up to 1,000, this is still the same. I've only bumped this by 1 right here. Okay, that's the difference of being from that to here. Now I'm going to do one, I'm going to really jump up. I'm going to go all the way to 1,000,000. And I get this to be 2.71828. So notice from here to here, these are the same. This only went up to this. And basically, this is the number that we're going to stick with. Okay, this is pretty close. Okay, this number, when this approaches infinity, this, as x goes to infinity, we're going to call this e. And it's a big decimal number. The bigger we get, the closer we, the decimal places kind of extend out and we get more and more accurate. But this value, whatever that value is as it goes to infinity, that's just e. Okay. If you do on your calculators, you'll see this thing, and then you can just, sometimes it'll just keep it as e, and then you can do the approximate, and then it breaks it out as 2.718. Sometimes I do like e to the 1 or something, and I get that value. Okay. But it's on most of your calculators at 5. If I go here, there's the e to the x function, so I got to go second, e to the x, and e to the 1 would be what I was started with. Okay. We'll use this. So this letter E stands for 2.718. It's in your calculator. The calculator understands it. You just have to access it correctly. And you are graphing. So for that base, this is what you will frequently see in a model, in a math model. Okay. And later on, it turns out that we can get any math model into this. We'll talk about that later when we talk about logarithms, but it just kind of changes some things, but it kind of looks the very same thing. So the general form is e to the kx, and this thing kind of gets us to make it look like a 2 or 3 or 4. We'll talk about that later. Okay. So this would be a growth, k greater than 0, and then, so this is naturally the function, e to the minus kx, k is still greater than 0, but this would be decay. When you see a negative in here, negative 0.136 times x, it's going to be a decay. Round to 4 decimal places, this is just calculator. So I would say on my calculator, second, I would find my e to the x, and I think that's it. So my e to the x, and then I would do squared the 2 and hit, and that would be 7.389. Okay, so all of that I do on calculators. Notice that I can even have negative. That would be, here's the decay. Here's getting smaller and smaller for e to the negative 3, e to the negative 4. The square root of 7, it is okay, irrational. We can do now decimal numbers in the exponent. We just have to do it by calculator. Okay, it's all numerical. E to the pi would be something like 2.718 to the 3.14. But calculator-wise, you're just going to find your e and then find your pi on the calculator as well. Okay. So if I were to do e to the pi, I would go second, find my e. So that was the exponent, and my pi is over here as a second function over here. So I do second, that would be my pi. That would be that number. Approximate, if I didn't have these things, I would do 2.718. Do my exponent again, that's my caret key, and then I would do the 3.14 to 2 decimals. And that gives me 23.896 compared to 23.148 if I let the calculator do maximum decimal places for it. Okay. All right. So that's how we handle those. Graphing the graph of e to the x, let's just go ahead and go over here. There's no surprises once we do understand that it is just a base raised to a power. So y is equal to, now I'm going to do, it's saying what? Let me see if I can do my symbols. And now I have got, I should have an e in here. Let's see if it's in there. No. So it's just, they'll understand E. They understand E, so they just left it out of there. But now to the X. And there's no surprises. For 0, E to the 0, no matter what it is, it goes to 1. And then you can just look, well, you know it's got to go, E to the 1 is that 2.718. So here at 1, get it back down here. That's the 2.718, okay? And then we go up. If this was negative x, that's what it would be down. It would be a decay function as x gets bigger. And I wanted to look at this for just a second. So let me see if I do 1. Hopefully it's big enough that we can see it pretty quick. 1 over, and we may have to do a little differently here, 1 over x to the x. So as you see, this thing, don't worry about the negatives, I'm worried about this positive. You see that this thing kind of flattens out pretty quick, and that height, 2.699, and now if I did, let's go put 1,000 times. I'm just going to grow this up pretty quick. And this just gets it there faster, okay, because I'm multiplying it times here. Oh. It didn't do what I wanted it to do. Make sure there. Make sure it's doing what I'm thinking I want it to do. Nah. Yeah, that's what I wanted to do. It's just 1,000 times faster now it's getting there, and the height is the 2.718. See, that's pretty well fixed all the way through now. I just made it get there faster with the x's. Okay. Okay, so anytime I have these things, I'm looking for the base function. Do I see a base function anywhere? And what is this as far as transformation? It is the graph of e to the x, shifted right by 1, and then rotated around the, reflected across the x-axis. So if I started out with y is equal to e to the x, that gives me the base, and then all I'm going to do is move this thing over by 1, so minus 1 up. Let me get it in parentheses so it knows I'm still working with the exponent. So this is just shifted. Here's the 1. Shifted right by 1, so now that is the 1, 1. Instead of 0, 1, we move that point over. The 0, 1 is the one that I kind of reflect here. So if I go y is equal to e to the x, my 0 point, the y-intercept is the one that I'm going across. This point I know this is shifted right by 1. So it goes to there, and then I flip and do that across there. Shifted right by 1, and then I reflect it. Okay, so the biggest use, or one of the uses, one of our applications that we're going to do is focus on interest. And there's going to be 3, hold on just a second, let me see. Anyway, okay, so interest. I need to find so interest. What we have to worry about is there's a couple of different types of interest. So one type is I go and I kind of borrow some money to pay, like for furniture. So this is usually small things. Okay. And what they will do is say, okay, well, we're going to set you up a payment plan and we're going to charge you money to use our money. Okay. So the bank, you go to the bank, when you borrow money, you are having to pay them, and that's the interest. Okay. If you put money into savings, then they need to pay you interest for letting them use your money, because they're going to use your money even though it's in a savings account. They, do loans for cars. The bank would do loans for cars, mortgage payments for houses. Okay. But the very simple one, the way to do this is this simple interest, and the interest you weigh, this is called the simple. I'll call that in a minute. But the interest you pay it is just what the amount that you're going to do, the amount that you're taking a loan on, the interest rate, and for how long. So this is your interest cost. That's your cost. The amount that you have to pay them. This is the amount borrowed. And the P is for principal, the principal amount, your mortgage, the $2,000 for the furniture. Your R is your interest rate, and this is in decimal. So for 2%, you would be 0.02, okay? And then your T is your time, and this is understood to be in years. This interest rate is per year. Per year, this would be in years, and that would be your cost. That's a simple interest. This one is called simple interest. Okay. And then we're going to compound it. And what happens then, this is most likely you put money into a savings account. At the end of the year, your bank will give you some money. That's your interest payment for letting them use them. And then the next year, you've already got a little bit of interest. The next year, not only are they going to pay you, so you left everything alone, you're going to have the interest based on not only your original principal, but the interest that you have accumulated. Okay. The way that looks like is that this is called the amount you'll have. This is a little different. This isn't the interest, but this is the amount in T years. This is also called the future value, how much you will have in your account. Okay. And it is just the principal, the very same thing. What you started with, you leave it alone. R over N, I'm going to talk about the N in just a minute. This N is how many times they compound. Yearly, N is equal to 1. They've only do this thing one time. Okay. Semi-annual, twice a year. Semi-annual, every half a year. Okay. Quarterly, 4 times. They're going to do it each quarter, but they're only going to give you a piece of that interest. That's why this is. They don't give you the full interest. when they compound, but it works out to be a little better for you. And then monthly and daily, 365, so on. Okay. So that's compounding. We'll work some problems. And then finally, continuous. And that's the easiest one to use. Continuous, it is that they are constantly compounding, and for like by every second, you're basically doing the same every second. This is the best. Best. So this is first you want, then this, and then this is kind of like just, you don't want that. Because all they do is they never compound. They just give you this, they send you a check at the end of the year or whenever this time is for that interest, or you pay that over the length of that loan. Okay, so let's kind of work some problems with this. We need to know how to do this. These are good applications. And then later on, when we do logarithms, we're going to say, well, how long does it take us? And then the variable is in the exponent. Logs are going to enable us to answer that question. So I've got a principal amount. This is how we kind of break this thing out. Suppose that $15,000 is invested with 2.5% interest under the following options, compounding options. Okay. So determine the amount in the account at the end of 7 years. So I'm starting out with some amount, $15,000 in the account. I earn an interest rate of 0.025. Okay, that's 2.5% interest. 2 places to the left to give me the decimals. This is what I got to deal with. Okay, my time is 7 years. Okay, and now they're going to do us a compound annually. N is equal to 1. So at the end, my future value in that account is just going to be my principal, 1 plus R over N to the NT. That's my formula, so I just fill it in. 15,000, 1 plus 0.025. I'm only going to get it one time at the end of the year, and then 1 times 7. I'm going to emphasize that 1, even though that's just 7. So if we did this with that simple 1 time a year, but the next year I'm going to add a little bit to it. So this is grown by the interest rate, and then I'm going to do that. But this is going to be 15,000 times parentheses 1 plus 0.025 to the 1. 1 plus 0.025, I'm sorry, to the 7th. And I would have 17,830 and 29 cents. I always round dollars to 2 decimal places. A little more than what I started out with. Over those 7 years at 2.5%, I actually made $2,830 in interest. If I was doing the simple interest, they would have just said $2,830 if I'd have worked this thing out. They would just give me the interest, and I would have had the original one. So B, I'm compounding quarterly. Okay, so for quarterly, N is equal to 4 times 4 quarters. And it's the very same thing, but I'm going to write this out as 15,000, my A, 1 plus 0.025, because everything else is the same, except this is now 4, and this is now 4 times 7. It's 28. 1/4 the interest, but every time I'm now doing, for the next quarter, I'm actually earning a little better interest. This is a much better option of quarterly. Okay, so now I'm going to do this again. and I get $17,858.96. So I've made another 28 and change just by compounding quarterly at the end of the 7 years. I'm still in, so at 7 years. Here, at 7 years here. Okay. The more compounding, the more this grows, little bit by little bit. Every little bit helps when we're trying to retire. And now, but if I'm doing continuous, I'm doing this. So this is my original 15,000 E on my calculator, 0.025 times 7. So if I do that, e to the I get, let me slide this over for us, $17,868.69. So not a lot, but again, this is just on $15,000. This, no matter how many times I increase this, so if I went monthly, daily, hourly, this is still going to be kind of the limiting factor that I get. Okay, so if you look over here, that looks like that 1 plus 1 over x to the x. It looks very similar to it, and that kind of builds that number for the E. Okay, so these are the very same thing compounded annually. This is now we're starting with 8,000, 4.5%, so the R is 0.045 per year. This is after 5 years for each option, so kind of go through it annually. So N is equal to 1, quarterly N is equal to 4, monthly N is equal to 12, daily 365, and then PERT for the continuous, and that's how you would kind of build that out. Okay, so let's look at some other versions of calculations. Eventually, everything is going to go to some function, some initial amount e to the, we call this k, kt. Okay, but to get started, for certain ones, we're going to use just those basic functions. Okay, for like doubling, when you hear doubling time, doubling, then you know that some function is some initial 2 to the time. Okay, that's the doubling. Doubles every so often. And then another term is the half-life. So in a particular amount of time, every time I hit this certain thing, I've only got half of it left. And this would be, I start out with some initial amount for every time period, this is the H for a half-life. This is the doubling time. Every time I do this double, every 3 years is basically what I'm doing, and then doing that piece. I'll show you this in a minute. And then this is the very same thing, but it's the half-life, okay? So let's look at this in terms of this problem. Weapon-grade plutonium is composed of approximately 93% plutonium P-239, which is Pu-239, Okay, the half-life of Pu-239 is 24,000 years. Half-life, so that means every 24,000 years, whatever you started with, half of it is decayed. It throws off, all of the radioactive particles, and it just kind of decays out. The mass actually is reduced to energy. okay? So each 24,000. So this is what I'm telling you. So we started out with 0.5. A0, this is kind of the initial. This term, you'll see this a lot. This is the initial amount. The amount at time equal to 0. That's what this nomenclature is. So your A0 is 0.5 kilograms, and you know the half-life is 24,000. This is the model. So it is A0, 1/2, T divided by whatever they're giving you to the half-life, and they say this is 24,000. So you can write this model based on half-life, 1/2, by this, and this is what this is, 0.5, that's what they're doing right over here. 1/2, because we're talking about half-life, T over 24,000. So when we start out with T at time T is equal to 0, we run through, and only at time 24,000 do I hit one of these things. 1/2 to the 1 is 1, and I've only got a half of this left. I keep decaying down a little bit, but at 2 times this, which would be 48,000, 48,000 divided by this, I've gone through 2 half-lives, which are a half times a half, or 1/4 of this. And then this keeps working out. So it says evaluate these things. Let's just give me some extra room. What does A of 24,000 mean? It means interpret 0.5, 1/2, 24,000 divided by the half-life of 24,000. This 24,000 divided by 24,000 is 1. 1/2, 0.5 over 2, 0.5 over 2 would be 0.25. So you would only have this many kilograms left in 24,000, whatever this term is, the years. This needs to be in years as well. A of 72,000, the very same thing, 1/2. Now this is 72,000 divided by 24,000. And now this is 3. So this is, I started out with this is my A0, 1/2, but I've gone through 3 half-lives. 3 times I've reduced this, and I just hit the third one. So I would have 0.5 times 1/2 to the third, and this is 0.0625 kilograms. It's a half, another half that, and then a third half. I've gone through 3 times where I've halved, halved, halved. And that's what I've got left. A 2010 estimate of the population of Mexico is 111 million people with a projected growth rate of 0.994% per year. The growth rate. At this rate, the population in millions can be approximated. Now, this is, when they say this growth rate, that means you started with your initial and then you've added. If you just did the 0.994, that means you're kind of like decaying. This is less than, the B less than 1. So you really need to add a 1, and then this decimal number is the 0.00994. So P, the population at times T, this is what we think of this. The population at time T is the initial 111. The answer will be in millions, but you're just kind of reducing this thing off in T and 4 years. And then in 75 years, this would be P75. This would be the 75. Okay, so I'm going to let you work on those numbers. Here's half-lives again. So this one is growth. This one is half. You started with the initial 2, half. Every 30 years, you're going to half it. Okay. And this is growth, population growth, but you're only growing at 0.994% per year. This, you have to recognize that you had the initial plus a little bit extra that gives you the 1.00994. Okay, so take a look at those, see if you can work these through, see if you can set these up on your calculator, and I'll see you next time.